Wires are everywhere around us and we usually take them for granted. But have you ever wondered about the physics of a wire? How do electric fields follow a wire of arbitrary shape? Why do some wires work well for transporting energy and some work more like antennas? We can look at wires at different levels of abstraction. Most of the time we just treat a wire as a connection from one place to another. But sometimes if there's a lot of current, we might need to consider the resistance of the wire. If there's high frequency signals, we might model the wire as a transmission line. If the wire radiates a lot, we might model it as an antenna. Occasionally, if we don't know which circuit model to apply, we can analyze the electromagnetic fields in and around the wire. And very occasionally, we might need to think about individual electrons and nuclei. In this video, I'm going to focus on the electromagnetic picture. So I'm not going to talk much about voltage or current. Instead, I'm going to talk about electric and magnetic fields. And I'm not going to talk much about electrons or holes. I'm going to talk about abstract positive or negative charges. Here's a quick 30-second refresher on electric fields. A positive charge produces an outwards electric field, and a negative charge produces an inwards electric field. The field has a direction and magnitude at each point in space, and that tells us how much force would be exerted on a unit charge placed there. Say if we place the 1 coulomb test charge here near the positive charge, and it's repelled with 1 newton of force, we say the electric field is 1 newton per coulomb. If we have lots of charges, we just add up the fields from all the charges, and we end up with some overall field. If we draw lines following the arrows, notice that the field lines always start at positive charges, or infinity, and end at negative charges, or infinity. Back to wires. I'm going to start with a simple DC circuit with a battery and lamp. The lamp is just there as a load. The battery is going to be a magic battery that I can turn on in a controlled fashion, and I'm going to make the wires thick so we can see what's going on inside. Now let's simulate the electric field as I turn on the battery. The first thing we notice is that the electric field disturbance propagates outwards at the speed of light, both inside and outside the wires. The white arrows show direction and the shading shows magnitude. What I want to focus on first is the field inside the wires. Inside the wires, the electric field points along the wires everywhere. Let's watch the simulation from the start again. You can see even as the first disturbance propagates, which is long before there's any meaningful current, the electric field inside the wires immediately lines up with the wires. Why is that? Well, the short answer is feedback. Imagine if the electric field somewhere points in the wrong direction, let's say out of this corner. Charges will follow the electric field, but they can't fly out of the wire, so charge will build up on the surface of the wire, and the electric field of those charges will oppose the original field inside the wire. This feedback continues until the electric field is in the right direction to prevent further charge accumulation. That is, it must point along the wire. This happens very quickly, on the order of femtoseconds. Here is the calculated surface charge in our example circuit. One side of the circuit has become positive, and the other side has become negative. As I mentioned earlier, electric field lines go from positive charges to negative charges, and indeed that's the nature of the electric field here. That's the same electric field I showed before, it's just clearer if we understand where the source charges are. Now for another circuit, the division might not be geometrically down the middle. Here is a simulation with a more windy wire. But in general, some parts of a circuit will have positive surface charge, and some parts will have negative surface charge, and the electric field lines go between them. There's a very important thing that I want to point out here. The feedback mechanism is driven by the electric field inside the wire, but after the feedback, the electric field inside the wire is nearly zero. It's just enough to keep the current moving against the resistance of the wire. The result of the feedback is surface charges though, and the surface charges create a large electric field outside the wire. Almost all of the electric field is outside the wire. Now I want to look more closely at what happens when the voltage is changing. Say if instead of a battery we have an AC signal or a pulse generator. If you've understood the first half of this video, you might immediately say, well, the surface charges now change over time. And that's absolutely right. But to really understand how they evolve with time, we need to dig a bit deeper. And I'm actually going to use an even simpler circuit. Here's why. If you look at any real circuit in industry, there's almost always two conductors close together. You might have a coaxial cable or a twisted pair cable, or in a printed circuit board you have a ground plane that serves the role of the second wire. If you don't pair the conductors up like that, physics will do it for you, and it might be ugly. In the case of our toy circuit, the current here will be paired up with the so-called return current here. I use the term return current because that's what it's usually called, but it's a bit misleading because it suggests that the current has gone all the way around the circuit to get here, which is not really true. Remember my previous simulation, where you can see that the field disturbances, and hence current, propagate from the source on both sides. Anyway, because the two currents here run at a variable distance apart, the behavior will be different at different signal frequencies. The technical term is dispersion. For an educational example, I don't want that. So I'm going to use two parallel wires, and again I'm going to connect them to a magic pulse generator that will generate a voltage pulse, and I won't bother with a lamp now. I hear you say, wait a minute, Eigenmatt, that's not a complete circuit. But it doesn't matter for what I'm going to be looking at here. I mean, a capacitor is basically an open circuit too, and we put those in AC circuits all the time. Let's look at a simulation. I turn on the pulse generator, and a pulse of current flows down the wire pair. It travels mostly on the outside surfaces of the wires due to something called skin effect, but I'm not going to dwell on that in this video. At this point, the pulse is not affected at all by the open circuit. The circuit is 500 light picoseconds wide, or 15 centimeters in neurotypical units, and the simulation time is less than that, so no power of the pulse has reached the open circuit yet. But hang on, what is actually happening to make this pulse travel down the wire pair? Are electrons getting pushed into the circuit? And if they're getting pushed into one side, are they getting vacuumed up from the other side? Here's the problem with any of these pressure analogies. When we put a pulse down the wire pair, we find the velocity is approximately c, the speed of light in vacuum. Now I embed these same wires in plastic, and now the velocity of the pulse goes down by about half. That can't happen with billiard balls or water in a pipe. Any valid model has to include what's outside the wire, and the easiest way to do that is in terms of fields. Here's a simulation of the electric field when we send the pulse down our wire pair. That's beautiful, isn't it? Now here's the leap that might blow your mind. Remember we said that as a result of feedback, the electric field inside conducting wires is negligible, many magnitudes less than the field outside. We can approximate it as zero. Knowing that, and using Maxwell's equations, we can derive boundary conditions on the electric and magnetic fields at the boundary of the wires. Having those boundary conditions, we can now black box the wires. That is, we can completely ignore what's happening inside them. We simulate the fields traveling in free space between the wires, subject to the boundary conditions, and we get essentially the same result. To put it another way, we can treat wires as waveguides for waves that are traveling in the space around the wires. The boundary conditions on the wires help to guide the waves and contain them. Now, theoretically speaking, we don't have to use this field picture. We could instead calculate the forces between every charge in the system with the appropriate speed of light delays with all the charges in the surrounding medium, and it should give the same result. But this problem is a lot more tractable in terms of fields and waves in the fields. Once we have the fields, then we can calculate what the surface charges and currents in the wires must be to satisfy Maxwell's equations. Now let's continue this simulation and see what happens at the open end of the wires. The fields reflect off the open end, which is of course what we expect the voltage and current to do when they hit an open end. But if the fields are travelling in free space, why don't they just continue straight out of the open end? Well, it's to do with the geometry of the wires versus the wavelength of the waves. If the spacing is narrow, then the boundary conditions contain the waves and prevent them from escaping. If we make the spacing wider and the wavelength smaller, then more of the waves do continue out of the open end, and now we start to have an antenna. The details here are actually quite complex, so I'm going to delve into that more in another video. To summarize, in this video I looked at wires at the electromagnetic level. I showed you that there's a feedback mechanism which drives the electric field inside the wire to a near zero value, ultimately pointing along the wire, and the byproduct of that is surface charges and a large external electric field. And we can model the evolution of that electric field by treating the wires as a waveguide and looking at how waves propagate in the electric field. In practice, of course, we always need to choose the right level of abstraction for a given job. No one designs an iPhone by starting from electromagnetics, but sometimes it's useful to know how the underlying physics works so that we know when circuit abstractions break down. I hope you found this video interesting. Please like and subscribe if you want me to make more.